Welcome to today's session on best practices with Amazon Aurora. Just a bit of clarification, we are only going to be talking about Amazon Aurora for MySQL. When we were actually planning this talk, we had no idea that we were going to release Amazon Aurora for Postgres today. So it was a top secret, and even AWS guys didn't know. So everything that we are going to be talking about today is about Amazon Aurora for MySQL, and we will just talk about it as Amazon Aurora. And thanks for joining us for this session. I think the pub crawl just started, so love your enthusiasm for Aurora. So my name is Puneet Agrawal, and I'm a solutions architect at AWS. In my role, I help customers like yourselves architect applications on top of AWS. I also help customers adopt Amazon Aurora and other big data platforms. With me today, I have Steve Abraham. Steve is also a solutions architect at AWS, and he has quite a long background in databases and Amazon Aurora. And then we have Mario Kostelek, all the way from Ireland, joining us today to talk about his Aurora experience. Mario is a product engineer at Intercom, and well, he just got married last week, so let's give him a round of applause to congratulate him. Thanks for joining us, Mario. So we have 60 minutes of time. We will try to leave some time in the end to answer your questions. But all of us kind of get excited when talking about this stuff. So if we don't leave any time in the end, we'll be still around. So please come up and ask any questions that you have. So the purpose of today's talk is to give you Amazon Aurora best practices. This is a level 300 session. So we are going to assume that you already know about Amazon Aurora, you are already using Amazon Aurora, and you just want to know some of the best practices with Amazon Aurora. So we won't spend a lot of time in giving you a high-level overview. I'll basically talk about some of the migration best practices and performance best practices. Steve is going to cover some of our advanced use cases with Amazon Aurora. He's going to talk about real-time reporting and analytics. He'll also cover concurrent event stores use case, and he'll also talk about how our customers are integrating Amazon Aurora with other AWS services to create some really interesting and cool architectures. And then we'll welcome Mario from Intercom, who will talk about their journey to Amazon Aurora from MySQL and what types of challenges they faced and how they overcame those challenges. So just to recap very quickly what Amazon Aurora is, it's a MySQL-compatible relational database store. Right now, it's compatible with MySQL 5.6. It offers performance and availability of commercial database engines. You can do about 600,000 reads per second. You can do about 100,000 writes per second with R3 8 extra large box. And it offers you this performance at simplicity and cost effectiveness of open source database engines. If you watched the keynote today morning, you probably heard that we have 70 services and AWS is growing really fast. Amazon Aurora has been our fastest growing service for quite a few months now. So, and that's really because it is delivered as a managed service. There are no contracts to sign if you want an enterprise class database. You get your first database in less than 10 minutes. You pay as you go, standard AWS stuff. So we see wide customer adoption for this. In fact, top 100 AWS customers, out of that, 2/3 of them are using Amazon Aurora right now. So very popular database across AWS. So when it comes to Aurora and best practices, we don't really see a lot of questions from our customers around, well, how should we use the database? Aurora is pretty simple to use. It's MySQL compatible, and it just works for most of the customers. The only time we see questions coming from customers is, well, the first category is they want to understand how do they migrate to Aurora, right? So they want some guidance there. And when it comes to performance, they want to know how they should architect their applications to get most out of Aurora database. So I'll briefly cover those 2 points. So let's talk about migrations first. The choice of migration tool is very critical when you're moving to Aurora. or when you're moving to any other database, right? The choice of the tools will decide how much time does it take for you to migrate to Amazon Aurora, and how successful your migration project is, how much work you have to do in order to do that migration. So, for example, you could be migrating from RDS MySQL. There are a bunch of tools to help you with that. You could be migrating from MySQL or MariaDB or any other MySQL-compatible databases from EC2 or from your own data centers to Aurora. And we have another set of tools for that to help you with it. You could be migrating from Oracle or SQL Server to Aurora, which we see with a lot of customers. And we have other set of services that help you with that. Outside these services, you could still use native MySQL tools for migrations, or you could still do manual migration, or you could still use third-party tools. So this is not an exhaustive list of your options, but these are the options we think help our customers in successful migrations. So let's talk about these options quickly. If you are an RDS MySQL customer, the best and easiest way for you to adopt Amazon Aurora is you can use the database snapshot migration process. So what you do in this process is you just take a snapshot of your RDS MySQL database, and then you click a button and convert that snapshot into Amazon Aurora cluster, right? So the only thing you had to do, you probably already had a snapshot because you take backups, everybody's a good citizen, and you just click a button and you create a new cluster. Now, if you wanted to do a near zero downtime migration, you can also set up bin log replication from your source database to the target database. And that's something that our customers do right now by hand. In next 2 weeks, we will have a functionality that will let you set up that bin log replication automatically by a click of button. So by a click of button, you were able to migrate before, but now if you wanted to set up a bin log replication stream from your source to target database, you would be able to do that automatically. And I think we're launching that feature in second week of December. So let's say now you're running your MySQL databases on EC2 or in your own data centers. What our customers traditionally did in this case was they used native MySQL tools. So they used MySQL dump, MySQL loader, MySQL dumper, and other third-party tools. But what they saw was if their source database was big, like more than 1 terabyte, the migration time is significant. So they asked us to come up with some ways to speed up that migration. What we released a couple of months ago was binary snapshot ingestion feature for Amazon Aurora. So what you do in this feature is you install Percona's extra backup utility on your source database, EC2 or data center. You run a backup of your data files, right? IB data 0 or however you name your files. It will take a backup of your data files. You upload that backup to Amazon S3, and then you restore your database from that backup. And it's significantly faster than MySQL dump, for example, because it is not really replaying all of your DDL statements on Aurora. So I'll give you a quick demo of this. I think the font may not be readable, so just bear with me. What I'm doing here is I have a MySQL database on EC2. I'm creating a database in it. I already have bin log enabled. So I just created a database. Now I will download Percona's extra backup utility. So right now I'm installing the repo. I'm installing the utility, Percona extra backup. And now I run the backup command to actually take the backup of my MySQL database. And now I upload that backup to S3. So I'm just doing it from command line. It is at S3 now. So I go back to my console. I click a button, restore Aurora DB from S3. On the next page, I specify the source version. So right now, this utility supports source database 5.5 and 5.6. I select the S3 location. I specify an IAM role so that Aurora can access that S3 location. And then rest is standard, right? You just specify database identifier, master username and password. You specify your VPC, security groups. Database name, port, and other settings, and then you hit next. It will create your database. It will restore your database from S3. Of course, the restore time will depend on the size of your database, but it is significantly faster than native MySQL tools. So if you're looking to do a migration like this, definitely use Percona Extra Backup and this binary snapshot ingestion. If you wanted, so now database is being created. And you could still do replication from your source database to target database, right? After your Aurora database has been created, you can start bin log replication, and you can still do zero downtime migration. Couple of best practices with this method. Use file splitting and compression if your source database is big. The compression formats supported by this tool is gzip and Percona XBstream. There's a sample command on how to split that backup and how to gzip it. One thing that is important to note with this method is this method will move your schema and your data, but it won't move your user accounts, functions, and stored procedures automatically. So that's something that you will still need to export yourself and import into your MySQL database, which doesn't really take much time, right? Maybe 5 minutes. So that was about moving from MySQL-compatible databases to Amazon Aurora. What if you wanted to move from Oracle or SQL Server to Amazon Aurora? How does that look like? How many of you have done cross-platform migrations before? So quite a few people. And so you know it's not a simple process, right? There are essentially two things that you need to do. The first thing is you need to convert your schema from the source database to the target database, and that's where most of the work is involved, right? Many man days, months, and hours you spend in optimizing your schema. And the second part is once you have moved your schema over, you have to restore your data from your source database to your target database, right? So the two steps. So of course, you can use native tools to do it or third-party tools to do it. We see a lot of customers who do this manually, which has been done traditionally. Or you can use a couple of utilities, couple of services that we make available for you. So the first one is AWS Schema Conversion Tool. This tool connects to your source database. It will connect to your target Aurora database, and it will automatically convert your schema. I'll give you a demo of that, so I'll explain more. And the second service is AWS Database Migration Service. And this is a really cool service for what it does. This service can copy your data from your source database, let's say it's an Oracle database, and it can apply that data, restore that data into your target database, which could be Aurora or Postgres database. So it will take care of all the data type conversions and everything, right? You could do table level copy. There are a bunch of options there. The interesting thing is this tool can also do live replication from your source database to the target database. So let's say I'm an Oracle user and I'm running Oracle in production. If you tell me to use Aurora, I'll say that I'll really need to test it for at least a month, right? So what I want to do in that case is I'll let my production database running on Oracle. I'll do this migration. I'll set up replication from Oracle to Aurora, and then I'll test Aurora in parallel, right? So I'm testing my database on live data, on latest data, and after a month, if I feel comfortable, I can just stop the replication and point my applications to Amazon Aurora. Of course, your application may need to change because you're changing your database platform. But this tool makes it really easy for you to do this. If you're interested in these tools, there is a deep dive talk tomorrow on this, so definitely check that out. So let's do a quick demo of schema conversion tool. How does that look? So I have an Aurora and Oracle database in my console. I will just show you that I have a DMS sample schema in my Oracle database, which is about 8 gig in size. And then I'll connect to my Aurora database to show you that I don't have that DMS sample schema right now in my database. I opened Schema Conversion Tool, which is a desktop utility. It's a free utility. There are no charges for it. I connect to my source Oracle database, so I specify my username and password. Of course, your desktop needs to be able to connect to your source database, and it could be anywhere. It could be in your data center or on EC2. It could be anywhere. I'm testing the connection. I hit next, and when I do that, the tool looks into the Oracle database, looks at all the schemas. I will select the schema that I want to migrate to Aurora. And then it goes through all the database objects in the source Oracle database and figures out how well it can convert those things into Amazon Aurora. So this thing takes about 2 minutes. And this is, it really depends on how many objects you have, but 2 to 5 minutes maximum. Now, this is really important. This tool will give you a complete report of how well it will do when it migrates your code or converts your code. So this report, you can save it. This says that it can convert all your tables, but you will still need to make certain changes for your stored procedures. So now I connect to Amazon Aurora database. I see Amazon Aurora database to my right and Oracle to the left. I can convert that schema now. And when it converts the schema, it will tell me at what places exactly it wasn't able to convert the schema automatically. Because, of course, Oracle and MySQL has different features. So for this stored procedures, it is telling me that it doesn't support, Amazon Aurora doesn't support user types. So you directly know that this is what you need to do before you can migrate your schema. So, well, let's say I've done that and I apply the schema. Now I have transferred my schema to Amazon Aurora. And if I look at the databases to Amazon Aurora, I see DMS sample database. And if I list all the tables, I will see all the tables from that source Oracle database. So of course, it's not very straightforward in terms of moving from Oracle or SQL Server to Amazon Aurora as it is when you move from MySQL to Amazon Aurora. But this tool goes a long way in helping you decide if how much time it will take you to move to Amazon Aurora. So very helpful for our customers. Some of the other migration best practices, use the right migration approach. This will go a long way. We still see a lot of customers using native MySQL tools or other tools. Start with these tools, the recommended tools, and see if that works for you. You will be surprised how many customers we see who do not test their migration process. We see a lot of customers just migrating their production databases right away, and then they would have issues, and they'll open the tickets and all that. So it's great. We are happy to help our customers, but do migration and do testing of your migration process before you actually do production migration. Another best practice is you can consolidate your shards on Amazon Aurora. How many of you are running MySQL with multiple shards? It's a few people. Since Aurora has better scalability, performance, the number of, it supports up to 64 terabytes of storage, it really allows you to consolidate multiple shards on a single instance, or you can consolidate multiple smaller database on an Aurora instance. Of course, that improves your application logic. You don't have to manage multiple servers, so on and so forth. When you're doing schema conversion, after the conversion, look at your target schema and see if that schema needs further optimization. There are a couple of use cases where you may want to look at that schema and make some changes. For example, if you had any tables in the source database with longer columns, you may have to choose dynamic row format on Aurora. The way primary key is implemented in MySQL and Aurora is a little bit different than Oracle and SQL Server, so you may have to look into that as well. So that's why testing is really important. Let's talk about performance best practices. In order to get better performance out of your database, especially Amazon Aurora, you really need to understand what it is designed for. What are its performance characteristics? So Aurora is designed for highly concurrent, random access OLTP workloads. As you increase the number of connections, your performance should scale with number of connections. So you can throw hundreds and thousands of connections to Amazon Aurora. The performance remains consistent as you increase the number of tables, you increase the number of databases, as you increase your data set. The performance also remains consistent when you increase the number of Aurora read replicas. And these are some of the counterintuitive things if you're coming from MySQL, right? In MySQL, when you increase these things, performance usually degrades. And Aurora offers really low replication lag, almost negligible, so you can actually utilize your read replicas for your read workloads. So customers ask us, well, how should we performance test Aurora database? We have a white paper on this topic. The basic advice here is don't use just one client machine, use multiple client machines, open hundreds and thousands of connections from those machines. Use enhanced networking, make sure that you have good Linux kernel parameters, and then you can run your synthetic benchmarks, right, sysbench or anything else. But this also gives you a very good idea of how you should configure your applications to talk to Aurora to get best performance out of the database. So I would recommend looking at this white paper and going through some of the best practices there. Now, some general performance best practices. Since Aurora is MySQL compatible and it's delivered as a managed service, you don't really have to do a lot to get best performance out of the database. General database best practices still apply. You still want to create good indexes. You still want to run explain plans. You still want to use performance schema. All that stuff is still there. The important thing is you should leverage high concurrency with Aurora. If your application opens 10 connections to the Aurora database, you won't really unleash the power of the engine. If you have an opportunity to change your applications or re-architect your applications a little bit to open hundreds and thousands of connections and increase the total throughput of your application, that's when you will see huge performance improvements over MySQL and Amazon Aurora. So that's probably one of the most important points in getting the best performance out of Aurora. Read scaling, we already talked about it. Almost negligible replication lag. You don't have to overload your master databases. With all your read queries, you can use read replicas for your read workloads. Parameter tuning, this is interesting. So a lot of customers, and this is intuitive, right? If you're moving from MySQL to Aurora, you would want to move your configuration parameters from RDS MySQL to Aurora. Our advice is try not to do that. Some of the configuration parameters have different context in Aurora, and some of the configuration parameters do not even apply in Aurora. And that's because of the engine layer changes and the infrastructure layer changes that we have done in Aurora. So when you start an Aurora database, use the default parameters, and chances are you won't have to change those parameters. Of course, you can enable and disable certain features like bin log and all that using those parameters, but try not to change the performance-related parameters too much. When you're doing performance comparison, try not to look at CPU, memory, IOPS. Don't try to look at the system-level metrics when you're comparing performance between MySQL and Aurora, RDS MySQL and Aurora, or MySQL on EC2 and Aurora. Focus on what really matters to the application. So take a look at transactions per second. Think about selects per second, how many DDL and DML statements are going in per second. And you can do that. You can take a look at those metrics using CloudWatch. It gives you very good visibility into both system and database level metrics. Another best practice I will mention, keep query cache on. We have redesigned the query cache in Aurora, so it works really, really well as compared to MySQL. So most customers keep their query cache on with Amazon Aurora. But outside of these best practices, if you have highly concurrent workload, Aurora should just work for you. With that, let me hand it over to Steve, who will talk about some of the advanced use cases with Amazon Aurora.
All right. Well, thank you, Puneet. So, like Puneet said, we're going to get into some of the actual use cases and best practices around use cases using Amazon Aurora. So, I'd like to start with a scenario. We have a customer. This is an actual customer that we've worked with. It's a travel and booking industry customer. What they need is live contextual product recommendations. They need things like, recent airline airfare, hotel prices, things like that. They need to be able to deliver that in close to real time to their customers. We also have users that are on the other side, analysts, people that need to run reports and are interested in also getting this real-time information as well. They've got about 700 plus users internally, in addition to the users that are out on the internet that are hitting this database over and over again. We have about an 8 terabyte data set. And then another thing that's interesting to note is that the usage cycles over a 24-hour period. So, people are at work during the day, and that's when the analysts are there, these 700 people that are running reports. There's usually a higher number of people that are shopping and engaged during the day. And then we also want to take into consideration the cost. I mean, cost is something that always applies, and being able to maximize the efficiency of the resources that we use enables us to save a lot of the cost. So this is the original design. It's a pretty common thing that you would see anywhere else, where we have a storage backend with a database engine in front of it. And you can see we have our application users here, and everything's going well, and they're running the reports, and people are looking up airline airfare online, et cetera. And then what happens is that when more people come online, that we actually see that we start to overwhelm the database engine. And so the database engine itself has difficulty sometimes keeping up. And likewise, when those people leave, when they go home, then we still have this provisioned database infrastructure that no one is using, and it's sitting idle. So in that, we have wasted cost. So then what we do is we introduce Amazon Aurora and Aurora clusters. And so in this scenario, what we've done is we've replaced this with a DNS endpoint that's load balanced. And Puneet touched on this earlier, in that you can specify a single DNS endpoint for your read replicas. And with Aurora, you can have up to 15 read replicas behind that. And so it does load balancing. You can think of it as something similar to, but not the same thing as an elastic load balancer, in that it's a load balancer for your read-based queries. You still have a single read-write input for writing data to the database, but when we're talking about our analysts that want to run these queries against the database throughout the day, then that gives us an opportunity to do that. So as we are working with our analysts and as our traffic increases, so they come online, and so then what do we need to do from there? We need to scale up. And so we can add additional read replicas behind that read-only endpoint. And how do you do that? You could do it manually, or you could use CloudWatch. And with CloudWatch, you could automatically trigger the addition of these additional read replicas. Something that's unique and I think very powerful about Aurora is, given the Aurora storage engine is one shared storage engine that spans the entire region, when you bring on a read replica, you're just adding a compute head to already existing storage. That storage is the same. You don't have to replicate an additional copy of that data. It is the same data that's been replicated into 6 different locations across 3 different availability zones. So that gives you a great deal of read scalability. And then with this DNS endpoint that does the load balancing for you, it allows you to simplify your code by having your application always hit that same endpoint. So now when those users go home, then what we can do is we can scale down our Aurora cluster and save money during the off hours. And so that means that that line between resource allocation and resource consumption that we are so familiar with becomes much more closely matched with fewer gaps in between. So this is generally how you would implement this, is with this fleet scaling, as I just kind of described. So you can either use a scheduled job that reads the instance load metrics and calls Lambda, or you can create an alert, perhaps. But like I said, just tying back into CloudWatch and monitoring the load that's on your Aurora instances. And those additional instances are added or removed, and then our desired scale is achieved. And you can see that the the allocation and the consumption lines are very closely matched. So moving on from there, let's take a look at massively concurrent event stores. So in this scenario, we have a gaming industry customer. And this gaming industry customer needs to handle millions of requests per second, right? So they need to be able to scale very high. They need to have consistent latency. So whether they have a lot of users online at one time or a few users, they need to make sure that they have a consistent gaming experience for their customers. And of course, they're also concerned with cost as well. So traditionally, when we're talking about this type of scenario, NoSQL is where most people's minds go. And NoSQL is a good option. It's certainly, no one will fault you for using NoSQL. And it works very well under, a moderate or expected load. But then what happens sometimes with NoSQL is, due to the way that NoSQL databases are partitioned or sharded, you can occasionally get a hot partition. And that means that you also have sometimes the cold partitions. And in that scenario, that can impact the latency of your requests. And so, you can, in that specific instance, can actually degrade your performance. So with Aurora, like Puneet was saying, is designed to handle massive parallel queries. So we're talking about hundreds or thousands of active connections and upwards of 500,000 selects per second, 100,000 writes per second. So it can handle, what traditionally has fallen under the NoSQL category. But one of the nice things about Aurora is that you get consistent performance. You don't have that hot partition issue that you would sometimes have with a NoSQL database. So another thing to consider with this is the cost of NoSQL. So with NoSQL, you generally pay for and provision read and write capacity units when you're talking about that. And so that means that every time that you read and write from that NoSQL data store, you are consuming those reads. With Aurora, it's a little bit different, because Aurora has a couple of things going for it. One of them is that it has a buffer pool. It has memory. And so it's essentially a cache that's built right into Aurora, just like many other relational engines. And so your queries are not necessarily going to hit the disk when you query Aurora. A lot of those queries could be served up directly out of memory. And so that reduces the need that you have for disk I/O within Aurora. Another thing about Aurora is that you don't pre-provision storage or storage throughput. The storage throughput is delivered to you on an as-needed basis, and you're charged for it on an as-needed basis. So if you have low traffic and you are not consuming very many IOPS, or if the majority of your requests are being satisfied through what's in cache already, then you're not paying for or consuming any of those IOPS. And if your load increases and that you do need to go to disk, well, then you'll pay for it then. So it gives you an opportunity to both save on cost and performance when dealing with these massively concurrent workloads. So another thing that's unique about AWS and Aurora is that the services, a lot of services that we've developed at AWS, we build them with the mind that we have this whole AWS ecosystem. And we ask ourselves the question, how can we integrate with these so that we can provide a better service for our customers? So one of those ways, as it pertains to Aurora, is an event-driven data pipeline. So on the left here, you can see that we have some AWS services that are generating data. Maybe those are web servers that are generating log data. Maybe it's customer data that you're collecting. However you're generating your data, it's being generated on the left. And then as we move from left to right, we're putting that data into Amazon S3, which will serve as the basis for our data lake. When that file hits S3, then S3 can then fire a Lambda function. And that Lambda function that you can see there will then trigger Amazon Aurora to load that data directly from S3 into Aurora. So that means that automatically, as data is coming into your data lake, you can automate the loading of that data into S3, and you can also notify any pertinent users, anyone that might need to know, hey, we just got the latest dump of this data. Maybe we just got it from a customer. Maybe it's some data that we've been waiting for. And so now we know that that's online and that the S3 load has been completed. Another nice feature is the event-driven audit notification. So recently, it's been a few weeks now, we announced the integration of AWS Lambda with Amazon Aurora. And so what that means is that you can invoke a Lambda function from within the context of SQL statements inside of Aurora. So sounds interesting, but maybe you'd say, why would I use that? What would be the use case for that? Here is an example of one use case for that. Let's say that you have you have a monitored table. Maybe it's an important table because it has application settings in it, and you need to be notified if someone changes those application settings. Maybe in the example that we're going to see in the upcoming slides, you have a customer review table, and you want to know in close to real time, when customers are leaving you reviews and giving you feedback about your company or your service. And so what you can do is you could put a trigger on that table in Amazon Aurora, and when that trigger is fired, then it can invoke that Lambda function, which can then notify you or take any sort of custom action. So let's take a look at a quick demo here about Lambda integration. I'd like to first, before we get into the demo, describe what the architecture looks like for this demo. So on the left, we have our Aurora cluster, and then we have our table in that cluster, and it's our customer table, and we have a trigger on that table. And when that trigger is fired, it's going to call into AWS Lambda, right? Now, one thing to note about MySQL and Aurora in general is that the triggers are row-based rather than statement-based. And so that means that it's going to iterate through each one of those rows that change. So if you make a change and you update 1,000 rows in your table, that will translate into 1,000 Lambda invocations. So I would caution you to just keep that in mind while you're doing this. There's nothing necessarily wrong with that, but just be aware that that is how that works. So for us, what we want to know is we want to know when a customer leaves us a review in our table, we want to be notified. But if we have several of them that happen rapidly, we don't want to get 5, 10, 100, 1,000 emails all at once. Instead, we'd rather sort of batch those up and just get periodic emails. So what we're going to do is when the trigger fires, it will call AWS Lambda, which will then put that record into SQS. And then down on the parallel track, we have Amazon CloudWatch that is scheduling an AWS Lambda function that runs once per minute. And then that will go back to SQS, grab the batch of those requests that have been put in there, and then it will send out a notification via SNS. So right here, we're going to go ahead and create our SNS topic. In this case, we're going to have it create, it's called Aurora Mods is our topic. Once we have a topic, we create subscriptions. In this case, I'm just going to do an email subscription to my email address, but there are different mechanisms. You can send it through HTTP, you can send SMS messages, email, but we're just going to do my email address here. We're going to wait until I receive that email and confirm the subscription. So now I've confirmed it, and so you can see there's now a subscription ID that indicates that that is a valid subscription. Up here, we want to take note of this topic ARN, and we're going to reference this later on in our Lambda function, and that's how we know we're going to publish to this particular SNS topic. So now that we've created that, let's go to SQS. We're just going to create a simple queue here where we're going to queue up those messages. You can, in this particular use case, keep the default settings. We'll create the queue. And here we want to take note of the URL, which we will also use in our Lambda function in order to put those messages into that SQS queue. All right. So now we've created our SNS topic, a subscriber, we've created our SQS queue. So now let's get into Lambda. The first Lambda function we want to create is going to be the one that's going to respond to those trigger events. So we'll zoom in a little bit here on the screen so you can read it, hopefully. And so starting at the top, we're just going to do a couple of imports. We'll create an S3 client because we're using Bodo 3 with Python here. And then we're just going to send a message to that URL, the SQS URL that we just got from the previous step. That's all it is. We want to keep this function very lightweight so it can execute quickly and get out of there and return. So the next thing we're going to do is we're going to create the second Lambda function. And this one is the one that's going to be run on a regular schedule, the once per minute schedule. So again, here we import Bodo3. We create an SQS and an SNS client. Now we're going to pull the messages out of the SQS queue. If there are no messages, then we'll return. If there are, we'll create a buffer to accumulate the string that we'll be sending in our message. We're going to accumulate the messages that we just pulled out of that SQS queue. And then we're going to publish that to the SNS topic. You can see it's that ARN that we captured in the very first step that we did when we started all of this. Okay, so now that we've created that, now we need to schedule it with CloudWatch. So we'll add a trigger, and we will select CloudWatch Events, Schedule. We'll give it a rule name. So happens I have one called every 1 minute already. We'll give it a brief description. Executes every 1 minute. And then we will specify a cron expression that says that it's going to run once a minute, enable the trigger. And so now this Lambda function will run every minute, and it will pull that SQS queue, and we'll look for messages. Here we're going to create our table in Aurora. It's got 2 columns, customer name, customer feedback. We create our trigger. It's fairly standard. But if you look down here, this is where we're calling mysql.lambda-async, and we're using the ARN to that first Lambda function, and we're creating a JSON string with the customer name and the customer feedback. And so for each row, it will call that Lambda function and pass that into the Lambda function. And now we're going to go ahead and add a couple of rows to that table. And so when we execute this, it'll put 2 rows into the table, one from customer 1 and 2. And then right here, you can see that we've got a message from Aurora Mods, which was our topic, and we have concatenated those 2 customer reviews into a single email. Like I said, it's worth noting that this case, we're just showing that it is an email, but it could also just as easily go to an SMS. You could receive it on your phone. You could hit an HTTP endpoint. If you needed to take some other action when this happened, this would be an opportunity to bake that into the code as well. And so with that, I'd like to hand it over to Mario.
Yeah, thanks. Hi, everybody. How many of you are actually running Aurora in production? Okay, how many of you are actually thinking about running it soon? Okay, great. As you can see, my name is Mario. I like to believe that my job in Intercom is to solve problems. It seems that they don't agree. My position is actually a product engineer. I'm here today to talk about how the biggest MySQL box just became too small for us. How we evaluated if Aurora is a good fit for us, and how we migrated there, and what we learned on the way there. So let's start with a very simple question. What is Intercom? How many people actually know for Intercom here? Okay, sad. So we are a product company. We are building a software, or to phrase it a little bit better and more correct, we're building a really good software that simplifies communication between your business and your customers. So we are making it better, simpler, faster, more sexy, whatever you want. So how we actually started using Aurora? When Intercom was small, something really weird happened to us. People actually started using our product. And they started even paying for that. So they started sending messages to their customers. And as we wanted them to send more messages, we actually developed different channels of communication. So at first, we just had a messenger that you could embed in your website. Then we added support for email communication. We added support for mobile SDK, so you can embed the messenger in your mobile app. And then we integrated with Twitter, Facebook, whatever channel you want. So there is one problem that arises here, actually. We are not Snapchat. All these messages people send, they don't have a TTL. We have to store them in a database and keep them there forever. So if you had started building your product the same time we have started, you would probably chose the same stack. So it's Rails for backend, whatever JS for frontend, and then you choose MySQL with Postgres for your database. So everything was quite simple at start. We had one Rails database connecting to just one MySQL box, and our customers were happy with our product. Our database got on fire, actually. So as the best solution, what we did is we moved to something that was massively parallel, right? Now, we actually got a bigger box. So our customers were even happier with our product. It was fast again, it was reliable. And then our database got on fire again. Naturally, we got a bigger box again. So the problem with that box was that it was actually R38XL. So I'm not sure if you know, but until today, it was actually the bigger box of MySQL. So what we did, we analyzed the table, we analyzed the database, and we figured out that one particular table was far more used than all other tables. And that was exactly the table that distinguishes us and Snapchat. It was a table where we store all these messages. So what we did is we actually just split one database into two. So we had one Rails app connecting to two different databases. And in one database, it was one table, no joins, all queries indexed, just that. Unicorns came back, and they were flying or whatever they do around. And solution was working great for us for next year. And then, same problem. So what's so slow now, right? All the queries are indexed. It's almost like a key value store. And then we did a very simple thing. We just run a simple count on the whole table. And we got a number that was actually bigger than 2 billion. So when you think about 2 billion rows problem in a single MySQL table, the first problem is that your data very possibly can't fit in RAM. And your second problem is also that your data can't fit in RAM. So because your data can't fit in RAM, eventually you have to go to disk. Because you have to go to disk, you actually have to read from something that's far slower than RAM, which means that your performance is far more unpredictable than you would expect. And we were able to live with that because the nature of the data that was stored there is that you have part of the data set that's actually hot, and that's like recent messages, recent conversations, and then you have all the old conversations that are very infrequently accessed. The big problem that we had was that we weren't able to change our table schema at all. And we last year shipped around 100 features, and you don't want to block any progress of the company just because you can't move one table to a new schema. So you could ask yourself, what is so special about us? Why? How other people are doing that? So when you start working with relational databases, what you usually do is you start with alter table statements. That's how you change the table schema. It's great until you figure out that you use a row-based storage, and that every time you add a new column, you actually have to copy the whole table somewhere else. That's all done automatically by the engine. So it means actually that the more table you have, the longer it takes for migration to happen. And during that time, your table is actually locked, which means that nobody except the migration can access the data. And it's totally acceptable when you start, because it takes, what, a few seconds? But for us, it would cause an outage every single time. So that just wasn't an option. When people usually come to the same scale of data set, we are talking about terabyte or a few terabytes data set, they use trigger-based migrations like Percona toolkit or something similar. And that does some magic in the background, not to go into details, but the problem of that approach is that it actually doubles the load on your database. And it was also working for us for some decent time, but at some point, our database wasn't able to handle production load and migration load. And we weren't too concerned, except the fact that the whole company was a little bit slowing down because of my team. But the problem was that we knew that our database is not able to handle 2x load. And 2x load for us, it's not something that happens in 10 years, it's something that happens in 6 months. So we had to solve that problem. And actually, that's the time when I joined. So all the things you heard, it could totally be a lie. You wouldn't know, I wouldn't know. That's like it. Okay. So when I joined, my first task was actually to replace that massive database with something else. And we were thinking about a few different options. The first one was DynamoDB. And that's kind of a database from our dream. It's fully managed. We don't have to do anything. We truly believe that we can spend our time better than running databases. The problem with that approach was that everything in that service would have to change, except the interface itself. And we didn't have enough time to go that way. So the second solution that naturally comes to the problem is partition your data if you can. And we are able to partition our data, but at that point, there was no version of MySQL that RDS was offering that support native partitioning. We could do that on an application level, but it's just something we don't want to do if we don't have to. And around that time, Amazon actually started advertising Aurora. So the question, of course, you have to ask yourself is Aurora a good fit for us? They were advertising stuff like it's 10x better for a load of some of their customers, but I don't care about the other customers of AWS. I just care about our database. So let's see what they actually advertised. Oh, I'm pretty sure actually that slide changed today. So they advertise fast, available and durable, highly scalable. Do we know any other database that's not advertising that? I don't know for any, except maybe durable, okay. So that was all good, but the biggest thing for us was actually it was MySQL 5.6 compatible. And that was the exact version of the database that we were running in production. What that meant for us is, you know, all these problems of previous approaches like DynamoDB or sharding it on our layer. So if we could just migrate from MySQL to something that looks like MySQL, we don't have to do anything. That's great, right? So we would just flip DNS pointers from the old database to a new one and hope that everything goes well. So not really. When you end in a situation like that, you have to test your load. And Puneet actually mentioned that they published a white paper on benchmarking Aurora, but all these tests are synthetic. I still don't get an answer like, is it good for me and my company or not? So I found that, oh, actually it's me. The only test that should matter to you is testing against your production load, especially for relational databases. Your access patterns could be quite complex. If you're testing key-value store, it's very likely that you could reuse results from somebody else. It's very likely that your performance could, I don't know, it could depend on the size of the key and the hotness of all keys and size of the values. So we had to test our database. How do you do that? So the first thing you have to do is actually to test your tools. And maybe it's not completely intuitive, but the fact that testing tools are just have tests in their names, it doesn't mean that they work. I had no idea what should I expect from these tools. I had no idea, should it just produce many log lines, hammer the database, have an iron cat flying around? No idea. So what I did is I actually downloaded the white paper from Amazon, and I wanted to just reproduce results they got. That would mean that I'm actually capable of reproducing it and maybe using it for something else. So downloaded the paper. First time it actually crashed, but then I got 8 R3XL instances shooting queries at single Aurora cluster, and it was slightly slower. I got to the point where I was able to reproduce 100,000 reads per second for the biggest instance of Aurora, but it was close enough. So then I thought, okay, I have to test for my load because that's why I'm here, right? So the ideal way of testing would be getting a snapshot of your database, creating database from that snapshot, recording queries that are going into your database, and then somehow replicating them. And that's really good as long as one node can replicate all these queries in correct node, at the correct pace. So the problem arises when you need 2 or more nodes. And when you enter that area, problem gets really messy. And I'm not sure about you, but that wasn't the problem I wanted to solve. Replicating all these queries distributed in correct order, good luck with that. So when you can't have exact results, you approximate, right? So we created an image of our load. Internally, we have a tool that for every query ever run in production records how many times it was run, where from, and what was the execution plan of the query. It's not actually every query, it's the shape of the query, so all values are obfuscated. Having that tool, I took top 3 queries for all types, like top 3 selects, top 3 inserts, top 3 updates. I calculated ratios in the overall load, and then I just played with some random number generators to make sure that they're represented in correct ratios. And then I just had to somehow shoot them. So the thing is, as I said, Sysbench, the tool that's used in the white paper provided by Amazon, it crashed. It crashed because I had to tweak some kernel limits to make sure that all CPU cores are part of network processing, and because of that and the fact that Sysbench had some race condition, it would never stop. I would never get all the results. And during that, I figured out that the plan for queries in Sysbench is actually just a Lua script. So what I did, I created a Lua script that represents our load. All these 9 queries that I had, I just played with Lua random number generator. And you can ask yourself, why 9? So these 9 queries actually represented more than 97% of our load. Okay. So after we were sure that we can run it in production, or after we believed that we would be able to run it in production, what we did is actually we established replication between our original production box and Aurora box that we wanted to move on. You can use binary logs for that. It's pretty straightforward. The initial creation of the database doesn't take less than an hour, like Puneet said. It actually took 12 hours. And then, just to stay on the safe side, we enabled the replication from that Aurora box to a third MySQL box. And the reason why we had that is because we wanted to stay on the safe side. We wanted to be able to roll back to the old engine. It is something that looks like MySQL, but you never know what could happen on the way there. So one thing that I learned as a young engineer during that action is writing a runbook. You should write a runbook because people make really bad decisions when they're under stress. The other stuff that I learned during that is write a really detailed runbook. So this is, of course, not the whole runbook. It's just a part of it. It actually consisted of, I think, more than 70 steps. And for example, one of these steps was we started the action on Friday. We had to put database in certain security groups. And on Monday, we had to check that security groups are actually still attached to the database. Why? Because all developers actually have the access to AWS console. So it's not that somebody would like to just abort our action. It's people do random stuff because they don't know what they're doing and they're clicking around. You know, mouses are not really the most accurate pointers that you have. So the other thing is, for example, it was so detailed that you had a number of tabs you have to open in the console. So we migrated successfully in 8 minutes of downtime. We lost no records. And we had, I don't know, I think less than 500 status codes, but that's not because we don't have enough traffic. It's actually just because we coordinated the action really well. So how does it work for us? It does work. We are running on 30 to 40% of our CPU. We had few bugs that Amazon fixed in the meantime. For example, one of them was during migrations that would be small enough that we could be able to run alter table statements, the metadata table would lock and it would never be unlocked. That would also cause an outage. I think that's fixed now. We haven't seen that. I think we saw that twice, and after that, we never saw that. And now I'll actually just show you some stuff that seems very obvious, but changes in the land of Aurora. So one thing is use secondaries when you can. And of course, everybody uses secondaries when they can. But the difference is that replication lag is now below 30 milliseconds for us. When we were using Aurora, MySQL, the problem we had was during a peak time, replication lag would actually go above half an hour. So that means if your master goes down, you better cry. The other thing is that you can use, so Aurora is actually so powerful that very often we don't even need to run our offline queries in Redshift. We can have Aurora secondary that has a lower priority for a failover, and we can run ad hoc queries there. It's mostly useful for developers, not for analytics. The second thing is you should check your drivers. So Aurora failover actually depends on DNS, and some drivers cache the resolution of that. That means that your application will not be able to detect new master as soon as it should be. So before you go there, you can ask people who actually are running the same setup, or even better, you can test failovers. It's possible Aurora has a support just to induce failovers yourself. And the third thing is build your tooling or buy it. For example, we use Vivid Cortex. Recently, we upgraded to 1.9. Performance schema was not fast enough before for us to attach Vivid Cortex with full diagnostics. Now it is. The other thing is it's still a database. It's still a database with extraordinary freedom of defining queries. So if you acquire some lock that blocks the database, it's going to go down. So build your tooling to protect yourself from developers and yourself. So what we don't have to do anymore. Cluster monitoring got far simpler. If you remember, I said that our replication lag was sometimes higher than half an hour. And because of that, we actually needed some monitoring in place to make sure that certain secondaries are pulled out from the cluster. Since replication lag is not a problem, we don't need some classes of cluster monitoring anymore. The other problem is parameter tweaking. It's not a problem anymore. We actually had a guy, his name was Danny, and he was tweaking MySQL parameters for us. Now we don't need Danny anymore. Danny is no harm done to Danny. He just moved to another team. He's still part of the company. Aurora is just so more forgiving than MySQL that we don't need to tweak these things. So after all of that, you could say that it's impossible to break it, right? We have so many records, our load is pretty high, and of course it's possible to break it. It's software, that's first, and the second thing, it's a database. You can always break a database. So in order to actually make it less probable, really try to do all of these things. Try to test your load, try to write a runbook to have a seamless migration, try to use secondaries. You'll have far more features that will be enabled to use secondaries than you had before. Check your drivers, because that's what talks with your database. And at the end, build your tooling to protect yourself from yourself. Thank you.